this next part of the activity, we're going to see about a property that enantiomers have that allows us to distinguish them. So as you can imagine, most things are pretty much identical for a pair of enantiomers. So as I mentioned here, two enantiomers have identical chemical properties towards achiral reagents. That is how they might react with sulfuric acid, how they behave in water. However, of course, they're going to have different reactivity with chiral reagents. And a good example of a chiral reagent would be an enzyme. As it turns out, two enantiomers have essentially identical physical properties. So they're going to have the same color, boiling point, melting point, but there's one physical property that is unique. And that's what's referred to as the optical rotation. And it boggles my mind how scientists in the 1840s and 50s figured out that enantiomers, without actually really having a model of a molecule, but enantiomers are going to rotate plane polarized light in a different way, because that's what optical rotation means. So to explain this a little bit further, I've made this diagram. Now, one of the things we say is a chiral compound is optically active. An achiral compound, a compound with a plane of symmetry, is optically inactive. So imagine that we've got this tube, and we have a source of light, and you'll see that it's a very specific source of light when we're really making this measurement, but right now it doesn't matter. And we send this light down the tube, and normal light is oscillating in all 360 degrees in terms of this circular tube. But let's say we then send that light through a polarizer. And most of us have seen polarizers in the sense of sunglasses that allows only certain planes of light to pass through. Now, after the light passes through, we then say that the light is plane polarized. It's actually only oscillating in one plane. So you can imagine the brightness of the light has been reduced tremendously. Now, if you pass this plane polarized light through some kind of sample, and in particular, if it's an achiral sample, so if you're just passing it through water, then it's going to come through the water in the exact same plane and orientation as it went in. So we say here the plane polarization has not changed. And we can set up a detector and take a look at what this looks like, and we know how the light was oriented in going in, and then we can see that it didn't change in coming out. So we can say, oh, the molecule or the solution here is optically inactive. By contrast, if we prepare a solution of an optically active compound, and many of our carbohydrates are optically active, our amino acids are optically active, so we make a solution of this and then we pass through plane polarized light. As it turns out, one enantiomer will rotate plane polarized light to a certain degree in a certain direction. And as you might imagine, the other enantiomer rotates plane polarized light to the same magnitude, but in opposite direction. We can measure the degree to which the plane polarized light has been rotated. So this is what we mean by optical activity. And by degree, that's what I'm referring to as the alpha here, the degree of rotation of plane polarized light. As it turns out, this used to be a technique to actually measure the concentration of a solution. The more concentrated the solution is, the more the light will be rotated. So this is why actually we have to normalize it. As you shall see when we go to do a calculation of how much does the light get rotated, we'll divide that number by the concentration so that we can compare values. So let me show you how we calculate what's referred to as the specific rotation for a compound. So the specific rotation for a compound is calculated using this formula. So the alpha here is the degree of rotation. The L refers to the length of the chamber. So by dividing by the length of the chamber, we're normalizing it for different instruments. And C here is the concentration of our solution in molarity. Now again, so we can standardize our measurements, we refer to the temperature at 20 degrees Celsius, and this D refers to the D line of a sodium lamp, a sodium vapor lamp. So you can see that it's quite a standardized measurement so that we can compare between different laboratories in terms of what the specific rotation is for a structure. So you can see I give some examples here. We've got the 2-methylbutane 1-ol, and of course these are enantiomers, and one of the enantiomers is the R and the other is the S. Remember that those are referred to as the absolute configuration, and they are man-made designations. It's just we agree that this is how we're going to label these different enantiomers. But what you also see here is plus and minus. So that's the physical measurement of optical rotation. And so as it turns out, the R 2-methylbutane 1-ol rotates plane polarized light in a positive direction. And of course its enantiomer rotates plane polarized light in a negative direction. By how much? Well, here are the values right here. Now, one of the things that I want to make perfectly clear is that there's no correlation between R and positive or S and negative. That is, there are many molecules that have the human designation of R, and yet they rotate plane polarized light in the negative direction. Okay, so the two are not correlated. That said, if in a particular molecule, if the positive is R, well then the negative has to be S. So this is why I say down here the sign for the specific rotation is unrelated to the absolute configuration. And in your note pack you have that as degrees. So there's some interesting calculations we can do with the specific rotation. So let's take a look. This is one of the few times where we actually ask you to do a calculation in organic chemistry. So this is a different set of enantiomers. We have the 2-bromobutane enantiomers. On the left-hand side, the S configuration, right-hand side, R configuration. And here's a good case in point. In this case, the S has a positive specific rotation, and the R has a negative specific rotation. Of course, they are to the same magnitude. Now, I'm giving you a new formula here, and this is referred to as the enantiomeric excess. So, if we had a racemic mixture, and we've already talked about what a racemic mixture is, it's a 50-50 mixture of a pair of enantiomers. So if we have a racemic mixture, we would expect that the specific rotation would actually be 0, because one enantiomer would cancel the other enantiomer's specific rotation. So actually, we would say a racemic mixture is optically inactive. But let's say we have a mixture of enantiomers where there's an excess of one over the other. You can imagine that the excess of one would pull the rotation either in the positive or negative direction. And we can calculate, well, how much excess is there of that particular enantiomer, and hence the calculation of enantiomeric excess. The formula is the observed specific rotation divided by the specific rotation of the pure enantiomer times 100%. Now, you'll have an opportunity of doing this calculation a number of times. I'm going to talk you through one example here. You have to be careful. There's a little trick that you need to pay attention to. So, if a sample of 2-bromobutane has an observed specific rotation of plus 9.2 degrees, oh, and by the way, these should be degrees as well, calculate the distribution of the enantiomers in the mixture. Now note the question here. It's not actually asking for the enantiomeric excess. It's asking for the distribution of the enantiomers. And you'll see the distinction in a minute. But one of the things to reflect is, well, which enantiomer is in excess? Well, because we have a positive specific rotation, or an observed positive specific rotation, then we know that the S enantiomer is in excess. So you need to keep that in mind. Okay, so now let's do the calculation of the enantiomeric excess. So this would be EE is equal to the observed. And by the way, this is a very simple calculation. You just need to be careful. And then divided by the specific rotation of the pure enantiomer, which of course would be the 23.1. If the observed specific rotation was negative, you wouldn't divide by the positive specific rotation of the pure enantiomer. You divide by the negative. So in other words, the enantiomeric excess must always be a positive number. times 100%. And so if you do this calculation to roughly two significant figures, you'd see that it comes to 40%. So the enantiomeric excess is 40%, but that's not the distribution of the enantiomers, because you have a remaining 60% that's optically inactive. So 60% is optically inactive. And it's not because there's nothing there, but it's because it's a racemic mixture of the two enantiomers. What we just calculated was for the S enantiomer, so the S positive enantiomer. Okay, so keep that in mind. And then in terms of this optically inactive 60%, well, 30% of that must be the S positive, and another 30% must be the R negative. So if we're asked to calculate the distribution, well, then we need to take this and this together to calculate the full amount of S positive that's present. So as a final conclusion, then, I'm going to write it down at the bottom here. Our S positive enantiomer would therefore be 70%, and naturally, of course, our R negative would equal 30%. So once again, you calculate the enantiomeric excess, but that's outside of the racemic mixture. By calculating the enantiomeric excess, you know how much racemic mixture you have, and you split that into two. Half of it will be one enantiomer, half of it will be the other enantiomer. Then we combine the two numbers together and get the total amount of the enantiomer that is in excess. As I say, we'll be doing more practice with this in our live sessions as well as in our homework sets.